Welcome to my YouTube channel. In this video, we are going to discuss on thermal conduction and thermal conductivity. So what is thermal conduction? Thermal conduction is a process by which heat is transferred through solids. So there are three main mechanisms of heat transfer. First is conduction. The transfer is through solid. Second is radiation. Okay, the transfer is without medium. And the third is convection, where the heat transfer is through liquid. Here are another example for heat transfer for three mechanisms. Conduction through solid, convection through liquid. Example here is air, and the third one is radiation through vacuum, or in other word, without a medium. For conduction, there are two ways for the heat to be transferred through solids. Which is, first is by lattice vibration and second is by collision of electrons. By lattice vibration, you can imagine like this, where the atoms are bound together, okay, by a force represented by a spring drawn here. So this is a network of atoms. For one side, if the heat is given, heat energy is given from one side of the network of the atoms, then it begins to vibrate, and then it transfers the vibration to the neighboring atoms, and it goes on transferring part by part, and lastly the whole structure vibrating. The second method is by collision of electrons. So first, the particles or electron from the hot side migrates to the cold side. Then they collide with each other. So the heat is transferred to the next particles. So now the two particles have similar energy levels and both are warm, and they move again to the other area, and the collision happen again. This animation shows how to imagine the vibration of lattice vibration. So every atom is physically bonded to its neighbors in some way. If heat energy is supplied to one part of a solid, the atoms vibrate faster. As they vibrate more, the bonds between atoms are shaken more. So this passes vibrations on to the next atom, and so on. Eventually, the energy spreads throughout the solid, and the overall temperature has increased. In collisions of electrons, all metals are good conductors of electricity. For a similar reason, they are also good conductors of heat. In metals, not only do atoms vibrate more when heated, but the free electrons charge around more as well. This transfers the energy much faster than just vibrations in bonds. So, the heat conduction through solid, especially in metal, there are two types: lattice vibration and collision of electrons. So the animation shows here the red circle here shows the vibration lattice vibration, and the blue circle represent the collision of electrons. So that is why the metal compared to other solid like wood or glass has higher heat condition. Okay, what is thermal conductivity? To compare the ability of the heat to be transferred through solid, we can refer to the thermal conductivity. Different metal or different material has different thermal conductivity. So thermal conductivity is defined as the negative rate of heat flow per unit area perpendicular to the flow per unit temperature gradient. So we are going to derive the thermal conductivity. These are examples of thermal conductivity for different material. For copper is 385 watt per Kelvin per meter. For cast iron, 80.40 watt per meter per Kelvin. So compare these two values. So copper has higher thermal conductivity. So this means that copper has better ability to transfer heat compared to cast iron. Instead of using unit watt per meter per Kelvin, watt per meter per degree Celsius also can be used. Compare with these two pens, one made from copper and one made from cast iron. So copper is the best or the better conductor compared to the cast iron by referring to the thermal conductivity value. Thermal conductivity is dependent on phase temperature, density, and molecular bending. So next we are going to derive of thermal conductivity. So let's say this is a rectangular block of metal. One surface here has temperature θ1 and at the other end of surface has temperature θ2. So θ1 is larger than θ2. In other words, θ1 is hotter compared to θ2. θ2 is cold. Therefore, the heat flow from hot to cold from left to right. Let's say the surface area is A, then the heat flow from one surface area to another surface area, so the distance traveled is delta x. So the temperature difference between the 2 points is delta theta, so we can define temperature gradient as rate of change in temperature with distance, which is written as negative delta theta per delta x. Negative shows that as the distance increases, the temperature decreases. So as delta x approach 0, we can write the temperature gradient as negative d theta by dx. Rate of heat flow is given by dq by dt. Heat energy Q, T is time taken. So it depends on cross-sectional area A, temperature gradient negative d theta by dx, and material of the solid. So we can write as dq by dt is directly proportional to negative a d theta by dx. Combine these two. And Using mathematics rule, when we put equal, so we must put a constant. So let us name the constant as k. So become negative ka d theta by dx. So k is defined by thermal conductivity. And this is called Fourier's law. So from this equation, we can rearrange, becomes k equals to negative dq by dt divided by a d theta by dx. So we can write a statement for thermal conductivity. Okay, thermal conductivity is defined as the negative rate of heat flow per unit area perpendicular to the flow per unit temperature gradient. So rate of heat flow is this one per unit area and perpendicular to the flow per unit temperature gradient. So the unit for K is dQ by dt is watt or joule per second, A is meter squared area, and d theta per dx, let's say we use unit Kelvin, per dx is meter. So we can cancel out this meter, becomes watt per meter per Kelvin. So as K increases, the rate of heat flow increases. So the higher the K, the higher the rate of heat flow, which means the better the conduction of the solid. Another word, the material is a good conductor with the large K. So let's try solve this example. The air in a room is at 25 degrees Celsius and outside is 0 degrees Celsius. So the window of the room has an area of 2 meters squared and thickness 2 millimeter. Calculate the rate of loss of heat by conduction through window. Thermal conductivity for glass is 1 watt per meter per degree Celsius. So given T1 25 degrees Celsius, T2 0 degrees Celsius, so the heat flow from hot to cold. So hot will be T1, cold will be T2. Area 2 meters squared, dx is 2 millimeter, and lastly K 1 watt per meter per degree Celsius. So using the rate of loss of heat, dq by dt, so equals to negative Ka d theta by dx. So we substitute 1, 2, and temperature T2 minus T final minus initial. So 0 minus 25, T2 minus T1, and divided by thickness 2 millimeter, convert to meter. So don't forget the negative, and the change in temperature is final minus initial. So the heat flow from hot to cold, so 0 minus 25. So the answer is 25 times 10 to the power of 3 watt. Okay, next we try the second example. One of the possible mechanisms of heat transfer in human body is conduction through a body fat. Suppose the heat travels through 0.03 meter of fat in reaching the skin, which has a total surface area of 1.7 meters squared and a temperature of 34 degrees Celsius. Find the amount of heat that reaches the skin in half an hour. If the temperature at the body interior is maintained at the normal value 37 degrees Celsius. Thermal conductivity of body fat is K equals to 0.2 joule per second per meter per degree Celsius. So dx is given 0.03, area is 1.7 meters squared, temperature 34 degrees Celsius, this is T2, time taken is half an hour, and this is T1, 37 degrees Celsius. So remember that the heat flow from hot to cold. So hot will be T1 and cold will be T2. And this is the K value. So using the equation dq per dt equals to negative Ka d theta by dx from Fourier's law. So we substitute the value of time taken, half an hour, convert to second. So 60 minutes is 30, half of 60 minutes for 1 hour is 30, then times 60 to get to convert to second. Then K value 0.2, area 1.2, hot to cold, so 34 minus 37 degrees Celsius divided by the distance traveled is 0.03. So the answer is Q equals to 6.1 times 10 to the power of 4 joule. However, heat transfer via blood flow to the skin is more effective and has the added advantage that the body can vary the blood flow as needed. Okay, the last example to be discussed, we read together the question. The temperature at the ends of a bar are 95 degrees Celsius at warmer end and 37 degrees Celsius at the cooler end. The length of the bar is 0.9 meter. What is the temperature at a point that is 0.3 meter from the cooler end of the bar? So, heat flow from hot to cold. So hot is T1 and cold is T2. 0.9 is the distance travel, dx, and this is dx1. So we are going to determine the next dx. We are going to determine the temperature at point 0.3 meter. So what is the next dx? 0.3 meter is measured from the cooler end of the bar. So imagine this is a bar. So from cooler end is here. This is where the heat is supplied. So therefore, the remainder of the length here is 0.6. So using the equation dq by dt equals to negative Ka d theta by dx, we can write two equations. So the first equation for which involve dx1, so dq by dt equals to negative Ka. So dq by dt is not given, K not given, A not given, but it happens all in the same rod, in the same bar. So we remain written the equation as dq by dt, K and A. So temperature from hot to cold. So hot is 95 degrees, cold is 37 degrees. Divided by 0.9 for the whole length of the bar. So this is equation 1. For the next distance, the heat travel to one point to the other point 0.3 from the end of the bar here. And we get 0.3 here. This is 0.6 actually. So typing error. Okay, 0.6. dx2 is 0.6. And dq by dt is the same because it happened in the same rod, and we assume no heat loss to the surrounding. So the rate of heat flow is the same. And then at equilibrium state, dq by dt is the same. So equals to negative K, same rod or same bar. Then cross-sectional area also the same because it happened at the same bar. Okay, hot to cold. So the temperature here, T1, is what we are going to determine. Here is 95 degrees at initial. divided by 0.6. So this is equation 2. Then we use ratio method to solve for T1. So 2 divided by 1. We can cancel out dq by dt, cancel out Ka. So we cross multiply to calculate for T1. The answer is 56.3 degrees Celsius. So therefore, the temperature is less than halfway between the temperature at warmer and cooler end. So this is 95, here is 37, so in between here is 56.3 degrees Celsius. Okay, that's all for my video. Thank you for watching. So please subscribe to my YouTube channel if you don't want to miss any of my video.